Hi everyone, I'm going to be talking about algorithm correctness today. We spent the whole of last week talking about complexity of algorithms. We talk about how to measure the speed of algorithms. We talk about worst case, average case, best case. We talk about complexity notations, all about algorithms in week 1. And week 2, all about correctness. And these are the two things that we're going to be discussing again and again for the rest of the semester in other topics. We also come back to complexity and correctness in most things that we do for the rest of the semester. But in general, we're going to be talking today is pretty independent to what we did last week, right? So complexity, correctness, we're doing correctness today. And thinking about correctness, you probably did a lot of mistakes when you were just starting to program back in first year or even before, especially when you first learn about if statements. It's very common for people to make mistakes when they're writing the first if statement. So for example, this program here, you're supposed to give yourself different points depending on what age you are. So if you're between, if you're younger than 30, then you give yourself 8 points. You're between 30 to 39, instead you give 7 points. 40 to 59, you give 5 points. And the code there, I can kind of see how the mistake came up, because maybe the writer thinking, oh, I'm less than 30, I give myself 8. If not, then I'm 540, I give myself 7. But of course, what problem is here is if you're less than 30, you're going to give yourself many, many, many points, which is the wrong thing to do. But this is like a common mistake that I see when on first year students. They're using if instead of else if when doing COM 105 or COM 1000 first time. You may think that professionals don't make that kind of mistake. Professionals are going to make a mistake with if and else statements. But let me show you code here. If you want to, you can pause this video and just take a look at the code and see if you can see mistake. So what it does is it's going to work out what year we are in right now. So year starts at 1980. And what happened is what I have is the number of days. So days is the number of days since January 1st, 1980. And you're supposed to work out how many years have passed since that year, since 1980. And the way this is done here is that if day is greater than 365, just keep on reducing by 365. Unless if it's a leap year, because if it's a leap year, you have to reduce by 366. So code looks pretty okay. I mean, just say the days is some big number, let's say 1000. What you do, you reduce by 365, like at the bottom here. So line 19 onwards. If it's not a leap year, you reduce by 365 and you increase year by 1. Sounds good. If it's a leap year, then you have to reduce by 366. Cool, good so far. So I don't know if you see the mistake yet. Keep on going. Now, the problem is, what if days actually is 366, exactly 366? I'm gonna go to days, is it greater than 365? Line 7, yeah, it is. Go to the leap year, is it leap year? It is. It actually is a leap year. So I go to line 12. So, okay, we're not going to go to that if statement in line 13 because we're at 366. Days actually is equal to 366. Okay, so we don't go there. And what do we do now? Wait, so days is equal to 366. Is it greater than 365? Yes. Okay. Past a while in line 7. Go to line 10. Is it a leap year? Yes, it is. Past line 10, go to line 12. Is it greater than 366? No, because it is 366. And now what you do? You're not going to go to that else statement at the bottom, because that's connected to the other if, not the inner if. What happened is you're stuck. You're an infinite loop. And you think, who wrote this code? Who would write such a code? Microsoft did. So a long time ago, more than a decade ago, there's something called a Zune. You don't think you've heard about a Zoom, but you probably heard about iPods a long time ago. Well, they still have a bit. They still have some iPods these days. Anyway, it's just a music player. And December 31st, 2008, every single first gen Microsoft Zoom stopped working because of that code. That's a leap year. That's a 366 day. And every Zoom couldn't work because they were stuck in an infinite loop when the machine started. Or I don't know, some routine and the machine just stopped. And Microsoft said, yeah, we understand. Just wait a day and it'll be okay the day after. And it did. The day after it was fine. If you want to look up more information about that, you can. Just go online, go Google Microsoft Zoom bug, and you can read the whole story on the internet. So, another bug. You probably have heard about the Y2K bug, but you probably haven't heard about this one. So in September 14, 3828, Windows will stop working. Well, actually, this is Windows XP. So if you're still somehow using Windows XP by the year 3828, it will stop working because the file time value in Windows uses a 64-bit value, and the date that it stores can only go up to September 14, 3828. I don't know why I'm picking on Microsoft today, but they have such good examples. And I want to tell you the story. And again, this is probably not a bug. This is probably a feature. Well, it stops you from using Windows XP in 3828. But there's a difference between this bug and the one before, because this one is not logical. This is about storage. And this is like me telling you a story about Psy. Like, if you know this guy. I mean, he got pretty famous. Well, I guess he got famous because he dances around in a nice way, but he's also famous because he's the guy who broke YouTube. Well, he didn't break it, but people broke YouTube because he is the reason why YouTube had to go from 32-bit to 64-bit in the view counter, because the view counter could only go up to like 2 billion, and well, he exceeded that. But really, to be honest, I just put him there because I want to share the story with you. Is it going to be relevant to what we're doing this week? No, not really, because the last two bugs that you saw is about implementation bug. We're going to be focusing on the first bug that you saw, like the Microsoft Zoom bug, because that is a logical bug and that is present in the algorithm. And we're going to be trying to catch that. We're going to be trying to catch algorithm errors. So how do we do that? How do you find errors in an algorithm? The best way is probably to not make any mistake in the first place. Like, seriously. Try to write simple and clear program that you can understand, break it down into small components, write good functions, all this stuff that you learn about writing good code. You do all that, you follow all the rules, then it will lessen the chance of you having a mistake and introducing bugs into your code. But of course, we can't always do that. So we do unit testing. You've been doing unit testing since you were in first year. You learn how to test different functions to make sure everything works. I mean, we do this a lot too in real life. We do this a lot at workplace. Unit testing, unit testing, unit testing. There's like test-driven development. And also another way you find errors is by doing code review. We don't do that when you're still a student in this university. But generally, when you start working, there'll be time when you have to sit down with your colleague, and he or she will check out your code. Well, you have to explain your code to your colleague, sometimes your boss, sometimes your manager, which can be a scary thing to do. You have to explain your code, explain how it works, and your colleague, your manager, whoever is going to listen in and try to spot bugs, or they're going to see, oh, does it make sense? Or can I see any mistakes? So that's what a code review is. And these are great software engineering tools, like unit testing, code review. This is how you find errors in the code in the workplace. But That's not what we're doing in this unit. This is not a software engineering unit. Our definition of a correct algorithm is that it will stop with the correct output for every possible input. And this is just something that you may not be able to pick up using unit testing. Because if there's an infinite number of possibilities, how are you going to cover them all with unit testing? And also you have to show that the algorithm actually stops. This is another thing which you cannot easily do using unit testing. You may have to work this out yourself. But of course, I'm still going to be using unit testing. Well, at least to test your assignments. And you can still use unit testing to see if your code actually works or not. But in general, when we want to prove an algorithm being correct, we are going to use mathematical proof. Well, not that mathematical. You're going to be using loop invariance for loops. So for algorithms that uses loops. And we're going to be using induction for algorithm that uses recursive functions. Now, this is like a prelude to something called formal methods. If you want to know more, you can check out the Wikipedia link there. Just be aware that it's pretty heavy stuff. You represent your program as mathematical objects, and then you use logic, you use mathematics to show the correctness between different states of your program. So it's quite theoretical. We're not going to go nowhere near there. We're just going to be using induction and loop invariance. And basically doing something that you already know. Proving that the code is correct. This is something that you already know at the back of your head. Like when you're running a code, you kind of know that it's correct. You have a feeling that it's correct at least. For example, this code here. It's a code that will find divisor of n. Can you read that code and see if it's correct? Like, you can at least show that it does stop. You can argue that it stops, right? And hopefully you can also argue that it produces the right answer. And you probably think that, I goes up from 2 to all the way up to n. And every time I hits a divisor, there's a if statement there. You're going to output something on the screen, right? You can show that, you can argue that it stops. You can argue that's probably correct. And yeah, that's pretty much proving the code. Like, you already know that the code is correct most of the time. You already feel it. We just need to put that into writing. Here's another one. Like, here's a code that will add x n times. This one is recursive. So we're going to be using induction for that. But again, you probably can feel that this code is correct. Right? If it does stop and it does add x for a number of times. So again, you kind of know already when the code is correct. You can argue to yourself. You can tell yourself that this is correct. So all you need to do now is learn some tools on how to do that properly, to actually put this into writing. And yeah, that can be hard. But this is just something that you already know how to do. Because again, if you can explain the code to yourself, if you can convince yourself that the code is correct, then I'm sure you can also convince other people. And you're going to pick up some tools that you can use to do that. But we're not a mathematics course, so we're not going to achieve the same level of formality. We'll still be somewhat informal when we're doing this. And in fact, if you can't write a proof formally, at least if you can still explain your code, you can argue about the correctness. You'll get some marks if the argument is correct. Well, I mean, obviously you get some more marks if you can write a nice proof, sure. Okay, but the most important thing here is that you're able to explain why your code is correct. And you don't have to give a formal proof. Just argue, just give a good argument why it is correct. Now, I talk about loop invariance and I talk about induction, but you also find other ways of proving things. For example, proof by contradiction. Hopefully you remember what Prim's algorithm is. So with the Prim's algorithm, you want to find the minimum spanning tree. And if you start with the green node, you will pick the edge that wave 2 there and connecting yourself to the orange node. And you ran across this algorithm back in Competitive 5, but I don't think we actually tried to prove that is correct. And that's something we can do now. This is actually easy to prove using proof by contradiction. I'm going to talk more about this when we talk about greedy algorithm. But for now, just to give you an idea how proof by contradiction work, I can just argue that, well, if you did not pick that edge that costs 2, well, let's say you pick the edge that costs 4, okay? Because you're making a spanning tree, eventually you will connect the middle node there, the one that was originally connected using the edge that costs 2, the middle one there. So you will eventually connect to that node using some other edges. I don't know which one, I don't care. But what I can do now is, if I take away the edge that costs 4, and I put in the edge that actually costs 2, well, now I have a spanning tree. The same is still a spanning tree, right? Because everything's still connected, but it costs less. So whatever you had earlier, it can't be a minimum spanning tree. So that's proof by contradiction. It's not induction. It's not loop invariance, but it's just another technique that you can use to prove correctness of algorithms. You may also be asked to show that an algorithm is incorrect, which is actually easier to do. Just go find some logical error, go find a mistake, or even easier, go find a counterexample. Find an example where the algorithm will give you the wrong answer, and you're done. So Skinner on page 14 has some tips on how to do this. It may not all make sense for now, but as we've progressed through the weeks, as you learn more and more topics, you'll be able to understand everything he says there. I know it's only page 14, but what he said there is pretty deep. So anyway, general tips when you want to see if a code is correct. First thing you do is get some intuition, do some random testing, go find counterexamples. Easiest thing to do, work out if the program actually finishes, like actually stops. Like what's the base case? When does it stop? Like it goes from n equals 1 to n equal to 0, or it goes to, or the counter goes up to n. Check out the behavior of the program for small inputs. See the behavior on consecutive runs. I mean, if it's a for loop, when I is equal to 5, then I goes to 6. What happens in between? What happens when I is about to finish? Go find the corner cases, and this is hard to do. You know, like the Microsoft student bug you saw at the start of the lecture. But yeah, these are the things that you can do to find errors in program, or to, well, if you can't find an error, then the sequence chant is correct. And finally, why you do this? Well, if you don't do research computer science, you're probably not going to be doing this in real life. But it's still good to know what can be done. Like, I guess my analogy here is like with Java. You've been learning Java for years now, and sometimes I gotta ask, like, what do you know about Maven? What do you know about Ant or Gradle? What do you know about jar files? And I think majority of students do not know Java that much. So yeah, you are learning Java, but you haven't learned all about Java. And same thing here, you gotta be learning about how to prove things, but just as a beginner, just to see bits and pieces. I mean, do we do this in real life? Do you prove that a code is correct in real life? If you're a web developer, probably not. You don't need to do something like that. If you're working for, like, if you make medical equipments, you make missile launchers or space rockets, and yeah, I hope so. You know, when the cost of failure is so expensive, then that is where you want to spend the effort to prove that the code is correct. So in these cases, testing just gets too expensive. If you want to launch the spaceships, you don't want to try it 1,000 times until you get it right. Especially not if someone's driving that spaceship. So you sit down, prove that the code is correct, make sure everything's right, and then you launch it once, and hopefully it works. If you want to know more, if you want to read more about what they do, the link earlier to the formal methods, they have some links to that shows you what people actually do in the real world when it comes to proofing code. I think I just have one final note here about correctness and optimality. Look, correctness is what we do in week 2. Optimality, we kind of talked about that last week. There are 2 different things. So, for example, here, like if I'm telling you, go find a spanning tree, and if I give you the tree on the right as the answer, what would you say? You're probably gonna say wrong. That's not the spanning tree. Well, no, it is actually a spanning tree. It's just it's not the minimum spanning tree. Okay, so if you're asked to prove that code is correct, then you can ask yourself, what is the problem? What is the problem it's trying to solve? Is it a search problem, decision problem, optimization? I mean, what you have here is they're both spanning trees. The one on the left is obviously the optimal one, but the one on the right is still a spanning tree. So the correctness of the algorithm depends on what the problem is. Like, well, obviously. But what I'm trying to say here is that if I ask you to show the correctness of a search algorithm, then don't try to prove that it produces the optimal answer. If my question is there a path between A and B? All right. I mean, here's a graph. Is there a path between A and B? And then you try to tell me the shortest path between A and B. If you try to prove that the code is finding the shortest path between A and B, then obviously you're not going to be able to do it. So be aware what the problem is, and when you show that an algorithm is correct, make sure you are showing the right thing. All right, so that's it for this week. Well, sorry, not for this week, for this lecture. Coming up next, I'm going to talk about induction, and then we're going to use induction to prove codes, then loop invariance, and again, we're going to use loop invariance to show the code is correct. Okay, so I'll see you in the next lecture.